All right, guys. Number 4. So, hey, we already did a video on 1, 2, and 3. Let me just remind you what we found out with number 1. So you got the worksheet in front of you, right? In number 1, what we found out that at all these points, point O, point A, B, C, D, what did we find out? The mechanical energy at all of those points is equal to 1 joule everywhere at all those points. Now look, why is that? I want to show you why that is. Well, the only forces affecting the motion, because notice the worksheet here says without friction. Everybody see those two words? Yeah. Without friction means that this toy van is going to move through the loop. You know, it's going to move around this course without losing any mechanical energy. Does that make sense? Yeah. The only forces affecting the motion of the toy van are gravity and spring. So therefore, mechanical energy initial equals mechanical energy final. You know, for any 2 points, you could say that O is the initial, O is the initial, and A is the final. Or you could say C is the initial and D is the final. It doesn't matter because mechanical energy is staying constant. So mechanical energy everywhere is 1 joule. Okay, so question 4. How far did the spring have to be compressed initially? So this spring was smushed some distance x. Can you guys visualize that? The toy car was smushed into the spring, right? Before it was released, before releasing the toy van, all the energy was in what form? Potential of spring. Like before the toy van got shot out, all the energy was in the form of potential of spring. What must that be equal to? 1 joule, because that's the mechanical energy everywhere, right? Does that make sense? Yep. So now, to solve number 4, we go potential energy of spring equals 1/2 kx squared. That's the equation for potential of spring. We have the spring constant right here, right? K of spring. So now we can solve for x. So x is going to be square root 2 times potential energy of spring over k. So that's going to be 2 times 1 joule over 200 newtons per meter, right? And then this comes out to be 0.1. The spring must have been compressed 0.1 meter. What? All right, number 5. Let's revert this. Any questions on 4? Okay, number 5. Suppose the level section of track after point D is a bed of sand. Ooh. Hey, man, after point D, if there was a bunch of sand up here, what would that introduce? Friction. Okay, and the bus comes to rest at point E. All right, so I'm going to draw the van right here at point E. There's the van at point E. Here's the van at point D. Okay? All right, what's the question? How much work did the sand do on the van between points D and E? So look, guys, what type of mechanical energy does the van have at point D? The mechanical energy at point D is equal to what? It's got kinetic, so we'll call that kinetic at D. Does it have potential? Yep. Well, because where did they tell us the 0 point was earlier? The 0 point's down here, so we'll just say plus potential at D. Okay, what type of energy, what are the mechanical energies at point E? Kinetic at E, do we have it? No, because why? What do they tell us in the problem? It stops at point E. So then plus potential at E. So what's the only energy we have at point E? Potential. What's the only energy we have at point D? We got kinetic and potential. Now look, if there was no friction from D to E, the energy would stay the same, right? But what does friction do? Does friction add energy or remove energy? Does friction add energy or remove energy? Removes it. Hey, what's the mechanical at point D going to add up to? It's going to be 1. Now look, what's the potential at point E? The potential at point E comes out to be 0.8. How would you calculate that? You're going to go mgh. M is 0.1, G is 10, H is 0.8. So that comes out to be 0.8. Yo.
If you have the HP 0,
Huh?
if you have the HP 0,
You could do that. Have up here be the 0 point? Yeah, you could do that. Earlier in the problem, it said to have down the bottom of the track be the 0 point. Okay?
What is the E subscript?
Point E. We got point D and point E. Okay? So look, how much energy was lost from point D to point E? 0.2, which is the answer. Friction did 0.2 joules of work. Look at, shh, watch. Mechanical energy at point D, shh. What's so funny?
It says P.
Huh?
It says P.
P?
At the top.
Hold on, guys. So look. Mechanical energy at D was 1. Mechanical energy at E, 0.8. So this must be negative 0.2.
We're so mature.